Hi, good morning. I'm Alekia Dagatla, Thermal Engineer at Hyve Solutions, and my topic is closed-loop cooling for high-performance compute systems. To summarize my abstract, I will be presenting a scalable liquid cooling solution applicable to hyperscale data centers, enabling higher power density and efficiency. You can read the full abstract on the site under my profile. Liquid cooling. The rise of artificial intelligence and the hardware that supports it is reshaping data centers' relationship with power density, and adopting liquid cooling at scale is likely a sign of things to come for hyperscale data centers in the near future. Need for liquid cooling. New hardware and AI workloads is packing more computing power into each piece of equipment, boosting the power density, the amount of electricity used by servers and storage in a rack, and the accompanying heat. This trend is challenging traditional practices in data center cooling and prompting data center operators to adapt new strategies and designs. Not only servers running these kind of workloads are harder to cool, but this increased demand for computing capacity tends to lead to a higher rack density, which is a recipe for overheating. Data centers across the globe are being mandated to simultaneously increase energy efficiency, consolidate operations, and reduce costs. In each year, data centers consume approximately 2% of the global power consumption. Image to the right shows the numbers for energy consumption by computing power. Some scenarios predict that computers will consume more power than the world can produce by 2040. Liquid cooling has come a long way. Today's liquid cooling technologies are more robust and energy efficient than ever, with lots of options to choose from. Images on the right show the different liquid cooling technologies that are available out there. Benefits of liquid cooling technology can be the ability to deploy at a higher density, a lower overall TCO driven by increased efficiency, and a greatly reduced footprint. When integrated with careful data center design, further gains can be achieved. Today's discussion will be focused on indirect liquid cooling. Images on the left and right shows the cooling solution that is applicable to a 2-socket, 4-socket, and an 8-socket shadow core configurations. A typical liquid cooling loop comprises of cold plates used in conjunction with pumps, heat exchanger, and tubes to circulate the liquid or coolant. In most cases, reservoirs and valves are used to control fluid volume and flow rate, and for this solution, reservoirs tanks were added to account for any coolant loss over time. The working principle behind liquid cooling loop is that the pump circulates the fluid in the loop, picking up heat from the processors to the cold plates, circulating through the internal channels of the cold plate, and dissipating the heat through the heat exchanger. You will have a better understanding of the design and setup in the next few slides. In order to test the design, I've used a thermal load board, image on the left, as a test vehicle to get the performance numbers. This load board can provide power to dummy DIMMs, the image on the right, with LEDs, and fans, and also house 4 sockets for processors. I've used heater blocks in place of processors to provide the necessary power and load. Liquid-cooled system setup. I've used a 1U chassis to house load board, liquid cooling modules, and fans, and used a foam to bypass any airflow. For this system, I've used 6 fans, 3 for each liquid cooling module, to provide the necessary airflow. 1, 2, 3, 4 represent locations for heaters, and attached thermocouples for the case to measure temperatures. In order to make a good comparison of liquid and air cooling solutions, I've used the same setup for air-cooled solution but swapped the liquid cooling modules with standard 1U air-cooled solution, air-cooled heat sinks that can support up to 250 watts of power. Also, I've used the same number of fans for this setup. I've tested both liquid and air-cooled setup in a thermal chamber set to 25°C ambient and 30°C ambient, varying the heater loads and fan PWM to maintain case temperatures at or below 70°C. Bar graph to the right shows the hottest case temperatures for both liquid and air-cooled setups, with fans at 80% PWM. This is the results for 25°C ambient with 50% CPU heat load and with same PWM for both liquid and air-cooled solutions setups. This slide shows the results for 25°C ambient with 30% CPU heat load and with 30% fan PWM. These are the results for 30°C ambient with 100% CPU heat load and 100% fan PWM. These are the results for 30°C ambient with 50% CPU heat load and 40% fan PWM in order to maintain TKs below 70°C. These are the results for 30°C ambient with 30% CPU heat load and 30% fan PWM. Based on the test data, air-cooled system would require at least 6 times its current value in order to maintain the same CFM per watt ratio as the liquid cooling system. Bringing liquid directly to the chip allows to cool more compute-intensive workloads, allowing the server to use a higher inlet temperature for the liquid, which can be extremely efficient. Today, as the number of servers continue to multiply and the power usage grows exponentially, liquid cooling remains the most efficient cooling solution. It enables higher density server racks and increases data center power usage effectiveness, which is a winning combination. Forced air cooling outlived its effectiveness, and now the industry gravitates towards warm water cooling to tap next generation server technologies while lowering PUE. Thank you for joining me today, and you can reach out to me for any questions you may have.